Hello everyone, I'm Devipya from IIT Guwahati. Me and my team will be presenting the paper titled Fast Core Scheduling with User-Space Process Abstraction. This work was published at SOSP 2024 by researchers from Tsinghua University. The core problem of this paper addresses that core switching between applications is very slow due to kernel involvement. Every time the CPU switches cores between applications, it traps into the kernel, which wastes valuable microseconds and reducing overall system efficiency. So the paper aims to make this core switching fast and safe entirely in user space, eliminating the kernel overhead. To understand why this problem matters so much, let's step back and see where the bottleneck really lies. Today's cloud system use very high-speed networks and new storage devices which can perform over a million operations per second. But the CPU hasn't improved at the same rate. This means that even though our hardware can send and store data very quickly, the CPU often becomes the bottleneck that limits performance. To reduce CPU overhead caused by traditional scheduling which involve kernel, systems like Farm and RAM Cloud bypass the kernel. That means they skip the operating system kernel and directly access the hardware from user space. They run with a run to completion model where each thread gets its own core and runs to the end of its work. While this gives excellent raw performance, it also has a big drawback of busy waiting of CPU and cores cannot be easily shared between the applications. So even when one app is idle, those CPU cycles are wasted. In cloud data centers, we usually run many applications together to save costs. This is called workload consolidation. We generally deal with two types of applications. One is latency critical apps and another best effort apps. Latency critical apps that are called LApps that must respond instantly, and best effort apps are B apps that use leftover CPU time. If we can share CPU cores between them, we save large amount of money and time. But kernel kernel bypass systems make sharing difficult because they rely on core binding and busy polling. And the Linux kernel scheduler is far too slow. It switches tasks only every few milliseconds, while modern apps need switching at the microsecond level. So after understanding why existing systems fall short, the authors of this paper took a bold step back and asked what if we could completely rethink how code switch between applications. What if we didn't need the kernel at all? That led us to the fundamental question of this research. Can CPU cores switch between processes entirely in user space without involving the kernel? Their answer is yes, and that led to the creation of uprocess. Uprocess allows multiple applications to run inside a single shared address space. So a CPU core can switch between them by executing a jump instruction without calling into the kernel at all. But big two big challenges appear: memory safety and preemption. Memory safety is the problem where process share one address space. They could accidentally overwrite each other's memory. The authors solve this using memory protection keys MPK, which give each process its own protected memory region. And the preemption problem is that in the kernel, the OS can interrupt a task anytime for fairness, but there was no way to do this purely in user space. The solution to this is user space interrupts, which let one user process safely interrupt another.
Hi, this is Likita. Now let's see the solution of core reallocation in user space bypassing the kernel. This is generally done by the abstraction of a process called uprocess. Uprocesses run multiple applications within a single shared memory space. So multiple uprocesses run on the same memory. So there is a requirement for the memory protection. This is generally done by the MPKs, memory protection keys. And multiple uprocesses are scheduled together in a scheduler. Log-free FIFO queues are maintained per CPU, which contains the threads that are to be executed in that CPU. There is a requirement for scheduling in two cases: imbalance in the CPU load and preemptive scheduling. The reallocation is generally done by passing an interrupt signal uinter to the victim core. Then victim core calls a pre-registered user space interrupt handler. The handler passes through a call gate, a controlled interface that temporarily increases the privilege level of the view process without invoking the kernel. In Colgate, the U process to be switched is decided by the cadence matrix. The address space is switched to the new U process. Address space is generally protected by a MPK, which permissions are modified according to the new process. Core reallocation. The core jumps to the new U process directly by a single jump instruction. Now let's see about the U interrupt. U interrupt is a mechanism by which two kernel threads communicate in user space. There are two kernel threads, sender and receiver. Receiver core has a UPID register, user posted interrupt descriptor, which contains the interrupt vector and description. Sender core has a UITT table, user interrupt target table, which stores the mapping between UPID and the information for routing interrupt. This is how generally the communication occurs. When a sender wants to send something interrupt to a receiver, sender core calls send UIPI with an index. The hardware checks UITT table with that index and sends the interrupt to the receiver UPID register. If the receiver is running, it sends a physical IPI into it, which causes user interrupt to that core. When a receiver receives a U interrupt, user interrupt generally calls user interrupt handler. Now let's see about the user interrupt handler. It generally calls call gate to increase its privilege level. This is how the call gate works. It attains the whole memory rights and privilege instructions are invoked and shared memory access is then returned. There are many attacks possible in this. Now let's see about the attacks possible in the above model. Control flow hijack attacks, which means entering the privilege area without permissions. Memory instructions can be modified in the privileged mode. So memory configuration system calls, which intend to make memory executable, are intercepted and prohibited. Changing PLT, procedure linkage table, which causes running of arbitrary code. So our model does not use PLT. Instead uses runtime function pointers in read-only message passing region and modification of return address on the stack, which also causes running of arbitrary code without returning. So the thread stack is switched to the protected runtime stack segment. These are the functions by which the above occurs. CPU ID to runtime map, which maps the CPU to the stack segment in runtime region. CPU ID to task map, which maps CPU cores to their tasks. Now let's see about the memory protection keys. MPK enforces a user space memory protection, which divides the processor's memory into 16 parts with a 4-bit field in a page table entry. Each core has a PKRU register holding the permissions for these regions. Access can be changed by a WR, PKRU or XR stop instructions. These instructions have a very low latency of around 11 to 260 cycles. Now let's see about the address space memory regions. There are four memory regions: U process region, runtime region, text region and message passing region. Now let's see about U process region. U process region contains U process data, stack, heap, except text. Each process owns a MPK which only has read and write permissions. Runtime region. This is a privileged region which contains scheduling primitives, memory allocation, and system level services. This is generally invisible to all U processes and can be accessed by passing through call gate. The protected stack segment is stored here. Text region. The text region are executable only. The constant data in the text region can be leaked. So the variables are stored in the protected data segment. Message passing region. Special memory area that provides the necessary information to the U processes. Contains mapping such as UPI ID to runtime map and UPI ID to task map.
Hi, myself this is Rohita. Now we will discuss about the vessel implementation. A vessel is a groundbreaking system that implements what the authors call the U-process abstraction. So now in this section we will discuss how actually the authors built a vessel. A vessel enables a fast kernel-free CPU scheduling. In practice terms, it means we can achieve sub-microsecond context switches between applications, completely bypassing the operating system kernel. This is a fundamental shift from how traditional systems work. Now in this slide you can observe the architecture of a vessel. Now moving on to the next slide. In this slide we can observe the core components of a vessel. Vessel achieves this through three carefully designed components working together. First, the manager. Think of this as a setup group that prepares the execution environment and allocates all the essential resources. Secondly, the runtime. This is where the magic happens, providing the APIs and abstractions that let processes run safely entirely in user space. And third, the scheduler, the brain that makes lightning fast decisions about what runs next. These three components form a complete scheduling ecosystem that operates independently of the Linux kernel. Now, moving on to the next slide. Here we can see about the vessel manager. This is a standalone program that handles the entire uProcess life cycle. Its first job is to create what's called SMAS, the Shared Memory Address Space, using the mmap system call. This shared space is crucial because it's what allows us to avoid expensive page table switches later. The manager also creates per core FIFO queues. These are the communication channels that we scheduler you will use. When you want to create the new U process, here's what happens. The manager first creates a traditional Linux process via fork and binds it to a specific CPU core. Then it allocates a protected memory region using special memory protection calls. Finally, it sends an initialization command through the FIFO queue, telling the process to load the real application. When it comes time to shut down, the manager simply broadcasts kill commands and reclaim all the resources. Now, now let's see about the vessel runtime, the mini OS. I call this the mini OS for a good reason. This component essentially implements operating system functionality entirely in user space without having any need of kernel. The program loader is a modified version of what you would find in a traditional OS. It performs static code inspection to block any illegal instructions that might compromise security. Uses a custom dynamic linker designed for the shared memory space and handles memory protection initialization. For memory management, Vessel integrates JMlock malloc but redirects it to use the uProcess regions we talked about earlier, completely replacing the traditional mmap and munmap system calls. Thread management is handled entirely in user space. The runtime maintains real-time maps of which threads are running on which cores and manages all the scheduling queues. And crucially, for maximum performance, we recommend kernel bypass for I/O operations. This means direct hardcore access for network and storage to avoid the expensive overthread of the system calls. Now let's see into the compatibility challenges and solutions. Now you might be wondering about compatibility with existing applications. This is where we have to make some careful design trade-offs. For folk semantics, we faced a fundamental problem. A child process cannot share the parent's SMAS due to address conflicts. Our solution was to create entirely new U processes with cloned memory spaces instead. And for the termination, there is a limitation because the Linux kernel only sees the traditional process, not our individual U process threads. So, thread level termination requires workarounds using advanced signaling. And for dynamic loading with DLOpen, we do support it, but with important security checks. The runtime inspects all new code before making it executable to prevent introducing vulnerabilities. These trade offs were necessary to achieve the performance gains we were targeting. And now moving to the last part, which is scheduling policy and advantages. Finally, let's talk about the scheduling advantages and that makes all this worthwhile. Vessel uses a one-level global scheduling policy, unlike system like Caladin that uses two-level scheduling. This means we have similar overhead whether we are doing load balancing within an application or reallocating cores between applications. We maintain per core FIFO queues that can contain mixed application threads and now we have a global best effort task queue for background workloads. The key advantage is proactive preemption without kernel trapping. When we need to preempt a thread, we don't trap into the terminal. We handle it entirely in user space using hardware interrupts. And the result? We can fill CPU gaps much more efficiently than conservative schedulers, achieving near ideal CPU utilization even with a bursty microsecond scale workloads. And in conclusion, Bazel represents a significant step forward in operating systems design by enabling truly fast core schedulings and entirely in user space. Through carefully integration of modern hardware features and innovation software architecture, we have created a system that can schedule CPU cores between applications with the sub-microsecond overhead.
Now, let's start with the experimental setup used to evaluate Puzzle. The authors ran tests on a dual-socket 32-core Intel Xeon Gold system with a 256 GB of RAM and a 100 GB network interface hardware that reflects real modern data centers. They combined latency-critical workloads such as Memcached and CLO with best effort compute-intensive workloads like LinPack and Membench. Vessel was evaluated against three baselines: Caledon, Arcane, and Linux Completely Fair Scheduler. Key metrics included throughput, tail latency, and overall core utilization, all critical for balancing responsiveness and CPU efficiency in shared environments. When Memcached ran together with LinPack, Vessel achieved roughly 8% higher throughput and 42% lower tail latency than Caledon. The reason is its sub-microsecond core switching. Whenever load spikes, Vessel sends a user space interrupt to preempt background work immediately without entering the kernel. Even when 10 latency sensitive applications share one core, Vessel keeps latency stable, while Caledon's throughput drops by about 25%. This shows that user space scheduling can deliver both high utilization and predictable quality of service under extreme collocation. Micro benchmarks highlight where this improvement comes from. Vessel's average context switch latency is only 0.16 microseconds compared to 2.1 microseconds for Caledon, which is approximately a 13x speedup. Because all U processes share one address space, cache and TLB entries stay hot. Cache miss rate drops from 4.6% to 0.04%. Throughput scales almost linearly up to 42 cores, showing that Vessel's design scales well across sockets. When controlling memory bandwidth, Vessel also achieves 43% higher total throughput and far more precise throttling than Linux C groups or Intel MBA. These numbers confirm that sub-microsecond switching yields tangible system-level gains. To put, to put these results in context, earlier systems like Shenango, Caledon, and Arcane ran their schedulers in user space, but still depended on the kernel for final core handoff. Hardware offload models such as Turbo and Ringleader rely on smart NICs, which add cost and complexity. Abstractions like lightweight context, shreds, or NU provide isolation but require application refactoring. Vessel standouts because it performs core scheduling completely in user space, achieving isolation through MPK, and still runs unmodified Linux libraries. It essentially bridges the gap between kernel bypass performance and OS level security. Let's study the key takeaways of this study. Vessel introduces uProcess, a new user space process abstraction combining memory protection keys for isolation with user space interrupts for preemption. This design enables sub-microsecond context switches, higher CPU utilization, and precise resource control, all without kernel changes. It redefines process management by proving that safe, efficient scheduling can live entirely in user space, matching the microsecond timescales of modern data center I/O. Let's critically evaluate the work. Strength-wise, Vessel elegantly eliminates kernel overhead while maintaining isolation, a balance few systems achieve. It also largely compatible with existing Linux applications. On other hand, it depends on hardware support. Current Intel CPUs expose only 16 MPK keys, and user space interrupts are still a new feature. Some functions like fork and dynamic library loading remain restricted. Future extensions could include dynamic MPK key management, tighter integration with the Linux scheduler, or even smart NICs or NPUs to further accelerate user space scheduling. These improvements could make Vessel practical across a wide range of platforms. To conclude, Vessel redefines process management for the microsecond era. It introduces uProcess, a new user space abstraction that unites hardware-based isolation with user space preemption. By exploiting memory protection keys and user space interrupts, Vessel enables sub-microsecond context switch up to 13 times faster than Caledon and about 40% higher throughput in mixed workloads. The takeaway is clear. Core scheduling no longer has to live inside the kernel. With modern hardware support, user space runtimes can achieve the same safety with far greater efficiency. Vessel points toward a new generation of data center operating systems optimized for microsecond scale computing. Thank you for listening.